So our second speaker is Professor Benny Chor, the head of the computer science department. Are you department or school? School. In Tel Aviv University. Benny has joined the School of Computer Science in 2001, and before that he was a member in the Faculty of Computer Science at the Technion. He has made a fundamental contribution to the field of cryptography, and specifically to the study of information theoretic security. He's currently interested in computational biology, in privacy, randomness, and in educational aspects of computer science from primary school to university level. You should watch his new course. It's online with Amir Rubinstein.
In Hebrew.
In Hebrew, right. The Hebrew speakers, you watch it, and he will tell us about how to identify relatives privately, right?
Almost privately.
Almost privately.
Okay.
Almost relatives or almost privately?
Both. Okay, thanks Benny, and thanks the organizers for asking me to come. So the title of the talk is Identifying Relatives Almost Privately, and this is joint work with Orit Moskovich, who was my master's student here, and Benny Pinkas, who was my master's student at Technion many years ago. Okay, so there will be two parts to this talk. The first one is privacy and security aspects in personal genomic data. So I'll give some general, comments and information about that, and then I'll zoom into a specific problem about identifying relatives privately, and I'll introduce some new model for that. Okay, so probably most of you, I don't know if you're a computer scientist or physicist or whatever, but you're all aware of the revolution we had in communication and computers and so on, and it has, all sort of these social impacts. Not all of them so great. I'm not sure if you're happy about you or your kids, being in Facebook all the time and so on. So it's not only positive, but anyway, it happened. Okay, but there is a second revolution which many of you are not aware of. This is the biotech revolution, which goes sort of maybe not really under the hood, but it happens. I mean, amazing techniques were developed, reading our DNA that's already 20 years ago, and new ways to read it, and identifying diseases and so on. So this obviously it's known for people in life science or biotechnology, but it's not so much known to the general public. But my guess, and it's not only mine, it will be very well known in 5 to 15 years, because personal medicine will revolutionize the way our health is being treated. I mean, now I think if you go to a doctor once in a while, and what's the main difference between now and 30 years ago? Basically, the doctor head is in the computer, and it just looks there, right? But you don't feel any difference. But things are beginning to change. Drugs for all sort of cancer, these immunological treatment and so on. So things this will change. But with this huge change also comes maybe threats, but aspects to our own security. So I just mentioned a few bullets here, but there are many more. So I mean, the fact that it's very easy now to sequence and read all of your DNA also means that somebody who's interested in that, and it's very easy to have access to it, either at the lab if they take your blood, or just take a piece of hair from somebody, and I could sequence all of his or her DNA, and that could be undesirable. Biometric identification, there was a whole issue here in Israel, and it was decided that we do have biometric passports and ID cards. Not everybody is happy about that. Forensic techniques, using public genealogy site to solve crime cases, that's probably positive, but you could also see a negative side there. And then questions like cancer, genomic hubs. So there are many types of cancer where even a big hospital has 1 or 2 cases a year. So that's not enough to gather enough statistical information in order to do any treatment. So you want to gather information from many hospitals, but then there are privacy laws. I mean, you cannot just take, I think in the US it's very strict. You cannot just take information from one hospital, ship it to the other, and I mean, this will be against law. So what do? I mean, on one hand you want to cure, on the other hand you care about privacy. So, okay, so I want this is a huge area which is really developing hand in hand with our, our general privacy and security concerns, because we have this information which we didn't have, 30 years ago. I mean, we had DNA, but we didn't know how to read it. Okay, so I want to talk about a specific example, which is finding relatives, and that's actually not science fiction. There are companies like 23andMe and MyHeritage and so on. I mean, you give them $100, then you give them a test tube with your saliva, and they will sequence your DNA, and they will tell you who are your relatives. And in the past, they also used to predict your future. So what illness you're supposed to get, and so on. So I think later the FDA prevented it because it was too speculative. And suppose they tell me, I'm going to have a terrible brain tumor in 5 years, and there is nothing to do. So it's not clear if they want to know it. So they stopped doing this, but still they tell you you're, 50% Ashkenazi, 10% Neanderthal, all sort of things. This they do. Not everybody. Okay, so the old way of finding relatives, so, you go to to a place where there are organized records of marriage and so on, and you look through the records and you try to figure out who is, second cousin of whom and so on. So it's actually working, I think, in places like Iceland, where they had very good records of family, births, marriages, and so on. It works quite well. It's not very fast, and it's probably also restricted to these specific communities. Okay, the new way, that's something I took 2 years ago from the webpage of 23andMe. So they tell you it's very easy to get started in this process. Give me your money or credit card, and then I will send you a test tube. You spit into it. There's some powder you put into it. I guess it helps extracting the DNA. You shift it back to them. They sequence it, and so on. Okay, so everybody, not everybody, actually how people treat their privacy these days is not clear. I mean, the young people put their photos of them in all sort of weird, or not weird, but situations where maybe 10 years down the line they won't be happy about it. So people don't treat, let's say, people don't treat privacy the way people treat privacy, 30 years ago. But anyway. People do care about DNA because, definitely you could, among other things, you could predict, susceptibility to diseases and so on. So, and 23andMe and the other companies are worth it. So they say your privacy and security are important to us. I won't read the small letters there, but they say trust us. Whenever you see this, whenever you see this lock, you could trust us. There is a lock there. So we'll hide it and so on. So, okay, I'm joking, but okay. So maybe you trust them, but it also you have to trust, Ann Wozinski and Andy Page and all these guys who are founded 23andMe, and not only them, all the software engineers who they put the data. Do they encrypt it? Do they not encrypt it? Is it enough to encrypt it? Where is the key and so on? So there are questions. I'm not saying not to use it, but there are concerns there. And I don't think 23andMe, but some companies, maybe not only DNA, but their websites were hacked, and from information from credit card to personal information, whatever. What was it? Ashley? How is it called? They got anyway. There are many. You probably shouldn't trust rather than trust. Sorry? Yeah, Ashley Medicine. Right. Thanks. Okay. So the challenge is to solve this relative problem privately, and I should say it's a multi-party problem. So let's say 23andMe have 5 million customers. So basically, you want to do some protocol among these, or somebody should do some protocol among these 5 million customers. It's not just two customers. Okay, so our solution will employ some classical is mid-80s, tools from cryptography and secure multi-party computation, plus some basic knowledge about genetics and statistics and biological insights. Actually, I think we're really in a, not only in this, but in many things. Now we're really in an exciting era, because all these classical things, Byzantine agreement, encryption, so on, which were, when I played with these things back in the 80s, it was really intellectual games. So, we played this, and now they're becoming really implemented by big companies and so on. So things are really, we're in a shifting phase, and I'm sure in the audience there are people who know about it more than me. Okay, so I'll try to give some very basic background, maybe more on the biologic side than on the computer security side, and then describe some of the solution, some problems. Okay, so the basic thing we use, one basic thing we use is secure two-party computation. This goes back to Yao in 1982, first cast as the millionaire's problem. You have two participants, Alice and Bob, let's say. One has X, the other has Y. They want to compute the function f of xy, but they want to do it as if they give their information, their inputs to some trusted party, this guy with the beard, and he gives them back f of xy and nothing else. So f of xy is revealed, that's what they want to get, but nothing else, not whether x is. Nothing else except what can be inferred from f of xy, that you cannot prevent. Okay, so that's one thing, and so Yao gave a really beautiful protocol for this secure two-party computation, which achieves what I described. It's based on any trapdoor one-way function, and so again, back in '86 when we invented it, it looks like it's a great thing, but it will never be implemented. It's so complicated and so on. And now it is implemented. Maybe it's still a bit slow, but there are nice implementation, and this will definitely be better in a few years. So it's not science fiction anymore. Okay, a little bit about biological background. So crossing over and recombination. When you have when the next generation is generated, the chromosome, one we inherited from the father and one from the mother, they're getting parts of them getting mixed. This is this crossover, and what we give to the next generation is actually a mix of. It's not just pure father or mother, but it's a mixture of them. It's called crossing over, and that's the process called recombination. And the number of crossing over events per generation and their location are random variables, and the number of events is on the average between 2 to 4. And in general, close relatives will share long stretches of DNA, and as you go farther and farther, the shared stretches will be shorter. And these shared segments of the DNA are called identical by descent, or IBD. That's actually most of the techniques for identifying relatives are based on those, on how long and what's the distribution of these chunks of shared DNA. Okay, so this is a picture from Wikipedia, which sort of schematically shows how you have where is that? Let's say here, so this is the father, this is the mother. So the father, the chromosome that his son inherits is a mixture of this, and the same from the mother, and so on. And so as you see, when you have close relatives, I don't know, brothers or first cousins, so you've got long stretches which are shared, and the farther down the line you go, they become more and more mixed. Okay, the second thing I want to talk about is what's called SNPs. This is single nucleotide polymorphisms. These are locations in our DNA which we have mutations or differences, and much of our variations in the DNA we could just restrict to these single nucleotide polymorphism, and then usually there are just two dominant variants. 99% of it is either this or that. So you could really encode these SNPs as bits, 0 or 1. It makes life a bit easier. Okay, so basically, we are not the only ones or the first ones who worked on this problem. A team from UCLA, Eskin and Rafi Ostrovsky, and these guys worked on it, and they solved, they present the solution using fuzzy extractions. extractors. We use a different thing, but we share some of the ideas that they used. And one specific thing is looking at these, we reduce really the problem of counting intervals of identical SNPs. So instead of looking at all the bases of the DNA, we just look at these SNPs. We have a SNP about one in 1,000 bases. So it also is, instead of 3 billion, you just have 3 million, more or less. So that makes life a bit easier. Okay, so basically we have two people, we have their intervals of SNPs, and we want to do some, the counting of how many are shared. So we reduce the problem to this counting problem. We want to do it privately. We don't know how to do it completely privately, but almost privately. Okay, now there are two extreme solutions to this problem in general, a centralized one and a distributed one. The centralized one is the one used by the companies these days. You send all your DNA to these, to the company, they analyze it and give you back the results. You know, Benny and I are grandfather and academically, and I don't know, with Tal I have, well, maybe I have some relation. I don't know, Mickey Ben or who knows. Okay, no. Okay, anyway, so whether your relatives, they think you're relatives or not. So it's linear communication, which is good. It's the least you could have, but no privacy. That's not good. The other solution, which will be crazy, you cannot implement it, but I'll present it, is you have a full connectivity, and each suppose these are the customers of the company, so each pair of people will do this YAO protocol, whether they're relatives or not. Okay, so it will be perfectly private, but communication will be terrible. And if you think about 5 million customers, forget it. 5 million choose 2 is too much even for today's computers. Okay, so what we propose is something which is somewhere in the middle. Oops. Okay, so our model would be in the middle, somewhat a moderator model. There will be a moderator, like maybe the company representative, will give it some partial information, a limited number of bits. He will be able, based on that, to determine who with high probability are relatives or not, and then he will recommend to these guys who are presumably relatives to run this YAO protocol between themselves. So there will be much less communication, but some leakage of information. Okay, and the main technical challenge now is to estimate the size of sets intersection, where these sets will be intervals of these SNPs. Okay, so we want to estimate this size and do it privately or almost privately. We cut the intervals of these SNPs to, let's say, equal size intervals, let's say 300 bits each. And now we want to determine how many of these intervals are the same for the two users, and we want to do it privately. Okay, so one way to do it, I will not go too much into any of the mathematics, is this Jacquard similarity coefficient, which gives you an estimate of this intersection, and to do it privately, we employ some hash function, and basically we employ a hash function and use min hash, which is very popular technique. Larry Broder invented back in 1997, and it gives you an exact estimate of this Jacquard. The problem is that this is a random thing, and we do it just once, we'll get something which is completely unreliable, so we have to repeat it many times with many hash functions. Okay, so we assume that we have predetermined hash functions which are known to everybody, let's say H1 through HK. We compute, each party applies these hash functions to all of his intervals, finds the value which is minimal, and sends this value to the moderator. And the moderator counts how many of them are the same, how many of the minimum are the same. 3 minutes or 2 minutes? You are inconsistent. Okay, let me skip that, and that as well. So basically, instead of sending the whole intervals, we send just this min hash, and that's more economical. So we did some estimate based on some real biological data. So certain parameters which give us some low false positive and false negative value. We send about 20,000 bits instead of, if we send the whole thing, which it will be 17 million bits. So it's not negligible, but it's much less than the whole thing. Okay. Practical implementation of YAO, we use this CAPI protocol, which was developed in Bar-Ilan. You could do other things. They're reasonably fast, but still they require very strong machines. So they're not really practical today, but with technology becoming better, probably in a few years they will be okay. So technological impediments for our protocol. Okay, private DNA extraction is not obvious. I mean, if you go to your doctor and ask him to take your blood, then do I trust my doctor, right? If I'm paranoid, then I should be paranoid to the end. So now there are these sequencing things which are on the same size as a cell phone, and probably they cost $1,000 today, but they will cost less in 5 years. So I think if you're really paranoid, you could have these things and get your blood sequenced privately in your back room. Well, then somebody may watch from the side, but this, okay. Okay, so we believe this will be doable within 5 or 10 years. Okay, there is another problem, which it's not possible to solve, but I mean, if instead of my DNA, I don't know, I take Benny's DNA, and then I discover all sort of weird things about Benny, but this is hard to prevent, because I could get his hair and do it. So that's something that, I mean, it's not a problem of this protocol, it's sort of a general problem here. Okay, and maybe last thing, that's a related, but it's not the same. Maybe many of you heard that the FBI recently managed to solve all sort of crime cases from, I don't know, 40 years ago. They had the DNA, I don't know, of the rapist or something from then, and now with this 23andMe and so on, publishing all the data, they found out who their relatives are. He didn't give, so if they found his cousin and, I don't know, maybe his I don't know, something, they two cousins, and from that they could manage to find who he is. So that's sort of related, it's not the same problem, but it's related. And some companies, I think MyHeritage, refuses to give access to this data to the police. So it's an issue, right? If I give if I'm there in this thing, and then let's say my son murders somebody in 20 years, do I want my data to help the police catch him? I mean, obviously we see these things now and say it's great, we quote all these things, but so there are issues there. So okay, there are some open problems. I think I just want to say that this issue of privacy of data, which is related to privacy of biologically related data, is an issue people think about. And among other, there is a company that was established here, but there are many experts like Shafi and Vinod from MIT who are interested in solving such things in particular. Okay, and with that, Benny said I'm interested in computer science education, so I taught something close to Tamil Nadu about 4 or 5 years ago in some class. It was an amazing experience. Okay, thank you very much.